Okay, so another concept out of chapter 5, so fifth lecture out of chapter 5. So this is over compounds known as Meso compounds. So this would be an example of this molecule here with two alcohols. Doesn't matter that they're alcohols, it could be anything. Okay, so in this case, how many chiral carbons in the molecule? Well, that's a chiral carbon and that's a chiral carbon. So how many possible stereoisomers? So 2 to the n, so 2 to the n, so 2 to the 2 is 4 possible stereoisomers maximum. And again, from the last lecture, that could be the RR, the RS, the SR, or the SS isomer. Okay, so if we drew those 4 stereoisomers, so if we call this molecule A, so if we want to show 3 dimensions in stereochemistry, we need wedges, so we could put both OHs on a solid wedge. Or the first one could be on a solid and the second one could be on the dashed. Or the first one could be on the dashed and the second one could be on a solid wedge, or they could both be on dashed wedges. Right? That's the 4 possibilities. And so what I wanted to emphasize here, what's important to recognize. So if we take these 2 molecules, so they are mirror images of each other, right? So the blues reflect to blue, the whites reflect to white, and the green atoms reflect to green atoms. So those are mirror images. Are they superimposable? So if we do that, no, the blue and the white atoms do not match. But what if we do this? If I take this and turn it around 180 degrees, and now superimpose them on each other, right, now all of the atoms match. The whites line up, the blue line up, and the green line up. So this is a molecule that has 2 chiral carbons, right? Because this carbon has 4 different things attached, green, white, blue, and all of this. And this has green, white, blue, and all of this. So 2 chiral carbons, has a mirror image, but its mirror image is superimposable on itself. So this type of a molecule is what's known as a Meso compound. And so this molecule, even though it does have chiral carbons, is not optically active. If you remember what that means if you put this in a polarimeter, this would not rotate plane polarized light. And one way to think about that is that if this rotated plane polarized light one way, this would rotate it the other way, and they would cancel each other out, right? Okay, so if you have a Meso let's go back. So those are mirror images, but they are superimposable. If I took this molecule, it's got the same things attached, green, blue, and white to each of the carbons, but this molecule is not a mirror image, right? The blue atoms reflect, but then the green and white don't. And this is not superimposable. Let's see. Am I doing this right? Let me think. One second. Okay, so 2 chiral carbons, we can make one of the chiral centers match. Right, so this one matches, white, green, blue match, but then the back one doesn't. The whites match, but then the green and the blue do not match. So this has the same 4 groups on each chiral carbon, but it's not mirror images and it's not superimposable, so these 2 would be diastereomers of each other. But these 2, yes, so those 2 are mirror images of each other that are superimposable. So these are not enantiomers because they're superimposable. These are the same molecule. So what's unique about this molecule? To be a Meso compound, it has to have 2 chiral centers, but it's got an internal plane of symmetry. So you can see here, green reflects to green, blue reflects to blue, and white reflects to white. So that's a molecule. So any molecule that's got chiral carbons, but it's got an internal plane of symmetry, is a Meso compound, and it is not optically active. So how to see that plane of symmetry? So in these dash wedge forms, it's not obvious, but if we take this and rotate, so there's free rotation around carbon-carbon single bonds. So if we rotate around that bond 180 degrees, then the OH here that was behind the page, when you rotate 180 degrees, will come out of the page. So it'll now be on a solid wedge. And the hydrogen, which is out on the solid wedge, when you rotate 180 degrees, will go behind the piece of paper. So rotate 180 degrees, and that will give you this picture. And now you can see there's an internal plane of symmetry there, where both OHs are on the solid wedge. Or if we did the same there, rotate 180 degrees. So I keep one of the atoms the same, so basically what I'm doing. So the molecule is basically given to you like that. And so I'm going to rotate this 180 degrees so that you can see the two OHs then line up, and then the two hydrogens line up, and the two methyl groups line up, and now there's an internal plane of symmetry. Okay, so these two molecules have internal planes of symmetry. A and D do not have internal planes of symmetry because that's not a plane there, because the methyl group would not reflect into a methyl, right? And this methyl would not reflect into a methyl. So A and D do not have internal planes of symmetry. So if you have a Meso compound, there's 4 possible stereoisomers, but these two molecules are the same. Right, those are the ones that are mirror images, but they're superimposable on each other. So there's actually only A, B, and C different molecules. We'll call this D still, but B equals C. So if there's a Meso compound, then the formula is 2 to the n minus 1 is your possible is the maximum number of stereoisomers. Okay, so that's example. So if we took this molecule, for example, has that's a chiral carbon, that's a chiral carbon, that's not a chiral carbon, right? Because going this way is the same as going that way. So 2 possible 2 chiral carbons. So 2 to the 2 would be 4 possible stereoisomers, but you would have to recognize this could have a Meso compound because there is a plane of symmetry there. Where bromine lies in the plane, so it would not reflect into anything. So then this would only have 3 stereoisomers. Whereas this molecule, that's a chiral carbon, that's a chiral carbon, that's a chiral carbon, and there's no way to have a plane of symmetry here in this molecule. So 2 to the 3 would be 8. Would be 8 possible stereoisomers for that molecule. So again, anytime you have a Meso compound, you can take the formula 2 to the n and then subtract off 1, and that's the maximum number of stereoisomers. Okay, so how to recognize Meso compounds. So let's look at some other molecules and see if you can recognize, well, let's say a little bit more about this right quick. So if we compare what the ratio, so let's say A to B, A to C, A to D, B to C, so we'll call this B, and we'll call this C. B to D, so A to B, A to C, A to D, B to C, B to D, and C to D. That's the possible relationships, right? So what is A and B compared to each other? Are they enantiomers, diastereomers, or the same molecule? Well, let's see, this is 1, 2, 3, so this stereochemistry here is R. And this one is R. So I didn't do anything to this carbon, so this is still R, but this is now S. And compared to A, this has been flipped, so this is S, and nothing happened to that carbon, so it's still R, and this would be the S isomer. So A is AA, B is RS, or A is RR, B is RS, so these would have to be diastereomers, right? And the same is true for A to C. RR versus SR would be diastereomers, And if we compare A to D, RR to SS, A to D would be enantiomers, because each chiral carbon is opposite. And then if we compare B to C, so RS, SR, so you might want to say enantiomers, but that's not true in this case because it's a Meso compound. So B and C is same because it's Meso. And then B to D would be diastereomers, and C to D, SR to SS would be diastereomers. Right, so in this case, there's only one pair of enantiomers, because the other pair that would normally be enantiomer RS, SR is not, because it's a Meso compound. They're the same molecule. And I guess I made that point. Meso compounds not optically active, so the optical activity would be 0 degrees, right? It would not rotate plane polarized light. Okay, and so let's take these 1, 2, 3, 4, 6 molecules. Are they optically active or not? Well, to be optically active, it's got to have chiral carbons, and it cannot be a Meso compound. So this molecule has 2 chiral carbons, right? But is it Meso? Does it have an internal plane of symmetry? And the answer is yes. The plane of symmetry is right there, right? Chlorine would reflect to chlorine. Hydrogen would reflect to hydrogen. This CH2 would reflect to that one, and this CH2 would reflect to that one. So that's a Meso compound. So that's not optically active. So the cis isomer is not optically active, the trans isomer is, because now there is no plane of symmetry. So this is optically active. So if you stuck that in the polarimeter, it should rotate plane polarized light. This is not optically active. Okay, if we go to the 1,3 isomer, the cis, there is a plane of symmetry. It's right there. So the 2 CH2s in the plane don't reflect into anything because they're in the plane of symmetry. But this chlorine would reflect across the plane to that one. This would reflect across the plane to that, and this would reflect across the plane to that. So this is Meso. So that's not optically active. This is. So this is a chiral molecule. It is optically active. So it should rotate plane polarized light. Now that doesn't mean it has to rotate it much. It may rotate at 1 degrees, or it may rotate at 50 degrees. You just don't know until you sit down and make the measurement. Okay, how about the 1,4 isomer? Are they Meso compounds? Are they chiral or are they non-chiral? And so if we take this one, A versus B, is it a Meso compound? And the answer is no, not Meso. Why not? No chiral carbon, right? That's not a chiral carbon. That's not a chiral carbon. So it can't be Meso if it's not chiral. No chiral carbons. Does it have a plane of symmetry? Yes. That is a plane of symmetry where the chlorine and hydrogen lie in the plane. And that reflects to that, and that reflects to that. So it does have a plane of symmetry, but it does not have chiral carbons, so it's not a Meso compound. And neither is the trans isomer for the 1,4 isomer. No chiral carbons. So for the 1,4 isomer, neither of them are optically active. For the 1,3 isomer, the trans is. For the 1,2 isomer, the trans is chiral and optically active. Okay, so of course, if these are not the same things on those two atoms, so if it was cis 1,2, that would no longer be a Meso compound, right? Because chlorine would reflect into hydrogen, so there's no longer a plane of symmetry, so this is chiral and optically active. Okay, so we've looked at several different types of isomers now. We've looked at constitutional isomers. That's where atoms are attached in different order. So both of these are C2H6O, but the atoms are attached in totally different order. We looked at stereoisomers now, so enantiomers, non-superimposable mirror images. We looked at diastereomers, and we've looked at Meso compounds in this chapter. So diastereomers could be like RR versus SR, for example. So it could have to deal with chiral carbons, but it doesn't have to be chiral carbons. Right, we looked at alkenes, where if we had those two alkenes, one is trans, one is cis, those are diastereomers of each other, but these are a specific kind of diastereomers called geometric isomers. So this is going to refer to cis trans. And in later chapters, we'll see other examples of diastereomers called epimers and anomers, but we typically wouldn't talk about these until Organic Chemistry 2 when we talk about carbohydrates. And then we've looked at conformational isomers as well. And these differ by bond rotations. Right, for example, anti and gauche conformation or chair flip, those are bond rotations. So they change where atoms are at spatially as well, but they're not pertaining to chiral centers, or they're not pertaining to cis and trans. And these conformational isomers, right, you can rotate around bonds, so you can convert between one and the other. But for stereoisomers, you cannot convert one into the other without physically breaking a bond and remaking a bond. And the same goes for constitutional isomers. Okay, so chirality doesn't have to just be at carbon centers. It can be at other centers. Nitrogen can be chiral. Sulfurs can be chiral, for example. So if we take this molecule, that's a chiral nitrogen. And that's a chiral sulfur, right? They both have 4 different things attached. So that means we can assign stereochemistry, or R or S, to the nitrogen and the sulfur. So if we drew a Fischer projection here, so look into the wedge and draw what you see. So you would see the ethyl on the left and the chlorine on your right, and then you have a lone pair of electrons towards your head and a CH3 on bottom. So if we assign priorities, so assigning priorities again is based on mass, right? And so which of these has the highest mass is a chlorine. What has the lowest mass is electrons. So it's going to be number 4, and then the ethyl is number 2, and the methyl is number 3. So 1 to 2 to 3 is counterclockwise, that would be S. Number 4 is in the vertical position of the Fischer projection, so the arrow stays. So this would be the S isomer. So that's your answer. And the same is true for sulfur. So if we're standing over here looking at this molecule from that perspective, then what you would see is the oxygen towards your head, a lone pair of electrons on your right hand, and a methyl group on your left hand, and the propyl group towards your feet. And if you assign priorities, oxygen's number 1, propyl's number 2, methyl's number 3, lone pair of electrons number 4. So 1 to 2 to 3 is clockwise, number 4 is on the horizontal. So we're going to reverse the direction of the arrow, so that would be the S isomer as well. Okay, so typically in organic chemistry you might see chiral phosphorus, chiral sulfur, chiral nitrogen, but if it's chiral nitrogen, they're hard to isolate in their optically pure form because they rapidly undergo what's called inversion, where if you think of this like an umbrella with a gust of wind from the bottom and that flips inside out like an umbrella would, then you would get that. And if you drew a Fischer projection of this, right now you have that, and assign priorities 1, 2, 3, 4, and that would be S. Did I do this right? No, that's clockwise. That's R. Clockwise is R. So this is rapid process for amines. So they rapidly invert, and so you would end up then with a mixture of the R and S isomer. So if you remember the term for that, so if you have a 50-50 mixture of R and S isomers, that would be a racemic. Racemic mixture, so optical activity would be 0. So the point is, for amines, it's hard to isolate them in optically pure form because of the rapid inversion. But for chiral sulfur containing compounds and chiral phosphorus containing compounds, it's easy in some cases to isolate them in optically pure form. Okay. Okay, so that's it for this material. So one more lecture over this chapter, and then that would be the end of this chapter 5 stereochemistry material.